So we are going to be looking at equipment condition monitoring. We will see which maintenance strategy equipment condition monitoring belongs to. So under this section, we are going to look at the various maintenance strategy also, and the importance of equipment condition monitoring. So, what is equipment condition monitoring, and why is equipment condition monitoring very, very important to our operation, to the operations and maintenance of our facility? So we are going to see all of this in the course of this program. So under this module on equipment condition monitoring, we are going to be looking at one, introducing ourselves into the concept of equipment condition monitoring, knowing what it means, what it involves, and the various parameters that we really need to look at in monitoring the condition of our plant equipment and even our plant processes. So we are going to look at that. And then one of the equipment condition monitoring is vibration analysis. So we are going to look at vibration analysis, how to gather vibration information, that is how to collect data, how to analyze the information, and what kind of information we can glean from our vibration data. Okay, and also to the kind of equipment and the component of the equipment that we can monitor with vibration monitoring, or use that parameter vibration, the condition that we can use that parameter vibration to monitor. So we are also going to look at thermography. We are going to look at what it means, how infrared thermography is done, and what component of our plant facility we could apply the infrared thermography to, and which condition of the operating equipment or even our process that we can monitor with this condition monitoring technology. And of course, oil analysis. Okay, so we are going to look at the wear particle analysis and what information we can get from it, the oil chemistry, and also the contamination level of the oil. All of this is an indication of will give us an indication of the condition of the oil, okay, and of course the equipment, as to whether it is deteriorating or it is still operating normally. So we are going to see all of this, and then of course ultrasound or ultrasonic testing. What condition of the equipment we can use ultrasonic testing to actually monitor. Okay, so we'll see all of those, and then the most important of it all, after collecting the information, how do we know, or how do we use this information to determine the condition of our plant, our process, or our equipment? Okay, so we are going to look at the data that we collected and how we can analyze this data to get useful information from this data, and how we can also manage this data to get to improve the reliability of our plant. Then condition monitoring best practices. We are also going, what best practice, we are also going to look at them and then see how we can deploy them in our facility. So without wasting much of our time, let us go into the first aspect, which is the introduction to condition monitoring. But before we go into condition monitoring, for us to appreciate precisely the section of the maintenance strategy, or the type of maintenance strategy that condition monitoring falls into, in the first module we are going to introduce ourselves to condition monitoring, and under this introduction we are going to take an overview of condition monitoring, trying to determine what condition monitoring is and the various technology that we can use to monitor the condition of our plant processes. Okay, which falls under the types of condition monitoring. We are going to see that also. Then the condition monitoring processes or steps that we need to take in actually monitoring the condition of our plant, process, or equipment. So we are going to look at all of these in the course of this module. Okay, module 1. So let us look at the various maintenance strategies or the various forms of maintenance that we have that we can deploy in our facility. We have the run to failure. Okay, this is the earliest form of maintenance strategy. It's a maintenance strategy where you run the equipment till it fails. That is, you do not carry out any maintenance intervention until the equipment fails. Okay, so in such maintenance strategy, we know they have a lot of drawbacks, because when we have failure like that, it could, in most cases, be catastrophic, because it can affect other components or equipment downstream or upstream. So when that happens, that tends to increase the maintenance costs. Okay, and of course the time to restore such an equipment will also increase. So all these are various drawbacks to this form of maintenance strategy. So that is what you can see on your screen as you look at this photo. Okay, so you see that no maintenance intervention will be done until you have this kind of failure, until you have this coupling failed. That is when you say, okay, let us change this coupling. But the issue is that when this equipment is running and this fails while it is running, it can cause damage either to this gearbox or to other equipment downstream. Okay, so all of this will increase your maintenance time, increase your maintenance costs, and all of these constitute drawbacks. Then it could also happen that when this coupling fails, it can fail and seize this the shaft. Are we getting it? Once this shaft seizes, what happens to the motor? That can lead to the burnout of the motor. You see that in such an instant, you are not only going to replace the coupling, you are also going to replace the electric motor windings. Okay, so all of these will increase the maintenance cost. So that is a drawback. Are we getting it? So we have an improved form of maintenance also. Okay, which is the periodic or time-based maintenance. So in this kind of maintenance, we carry out our maintenance activity based on the time period. Okay, and that time period is based on the assumption that after that amount of time have elapsed, certain components in the equipment will have been going into the failure mode. So as you can see on your screen, let us assume that this vertical axis is housing, this vertical axis is the equipment condition or the component condition. So here we are actually looking at the vibration level. We know as the equipment is deteriorating, the vibration level will be increasing. So let's assume this vertical axis is the equipment condition, and then we have as against time on the horizontal axis. So all equipment is assumed that they follow this bathtub curve in their lifetime. Okay, so if you look at the initial time, you see that when the equipment is newly installed, the probability of failure is high. Okay, after some time, when the components are bedded in, the probability of failure becomes fairly stable until you get into the old age. Okay, where the equipment will be fast deteriorating. You see that the probability of failure will start increasing until the equipment will eventually fail. So we are just explaining this so that you will appreciate the concept of that time-based, okay, or periodic maintenance that you use to program your maintenance schedule or your PM schedule in your facility. So this is the assumption, okay. So here, which is the infant mortality stage, okay, any equipment that fails in this area fails when the equipment is fairly young or fairly new, okay. That failure in the infant stage could be as a result of wrong installation, as a result of installation-induced error, or malhandling, either in the store or warehouse or during transportation. So all of this will affect the early life of the equipment. So once the equipment survives that stage, it comes into the random failure stage, which is during the operational life of the equipment. Okay, so any equipment that fails within this period, it could be as a result of maybe maloperations, okay, or subjecting the equipment to stringent operating conditions that is outside the condition for which it is designed or installed. So that can cause failure within those areas. So outside that area, the old age region is when the equipment will start deteriorating naturally until it will eventually fail. So this is the infant mortality area, the random failure area, which is during the operational life, then the old age area, okay, or wear out region of the curve, okay, for that particular component. So the idea of preventive maintenance or time-based maintenance or periodic maintenance, okay, which is what we have here, is based on the fact that before it gets into this region, or as it's getting into this wear out region, before it eventually fails, we should do something. We should do change out of that component, okay, to bring the curve down back to its normal operating region. So you will see that in doing this, the equipment is not allowed to fail catastrophically or to run to failure, or the component is not allowed to run to failure. So if we assume that this curve is for a particular bearing, what it simply means is that as that bearing is entering the wear out region, okay, we do change out before it fails. As that seal, mechanical seal, is entering the wear out region, we do change out. Okay, as the insulation of the electrical equipment is entering this wear out region, we re-insulate. All is to bring the condition back to normal, that is, improve that condition or component of the equipment. So that is what the preventive maintenance program is based on. So from feedback from users, okay, and experiments carried out by manufacturers, they've known the amount of time it will take for a particular component, say bearing, seal, or what have you, okay, the amount of time it will take for the component to go into the wear out region if you subject them to a certain operational conditions. Are we getting it? So that is what informs the recommendation of the manufacturers on the change out interval or change out time. So it could be recommended that for this particular motor, okay, when you subject it to this kind of condition, after 2 months, 6 months, okay, or 2 years, do bearing change out. So that will now be what will inform your preventive maintenance program. That is what you will look at in designing your preventive maintenance program. Okay? So which means that if you are using this electric motor now in your facility, you could design your PM for the bearing change out to be every 2 years. So the assumption is that after 2 years of usage, that particular bearing will have been entering this wear out period. So before it gets beyond this wear out period to the point where it will eventually break down, do change out. Okay? So also it is for your lubricating oil. The assumption is that after this particular amount of time, if it is 3 months that is recommended for oil change out by the manufacturer, the assumption is that after that 3 months, the wear particle will have increased, which will eventually increase the wear rate, okay, within that particular engine. So at that time, do change out to renew or remove those wear particles that were there before, okay, and to improve the chemistry of the oil, so that the oil will now, the equipment will now operate as smooth again. Okay, so that is what informs the periodic or time-based maintenance program or preventive maintenance program. But there is a drawback in this. Okay, assuming that during normal operations there are offsets, which is very possible in the course of operation, and that offset introduces stringent operational conditions, okay, that overstress that component or the equipment in general, what will happen? It means that the equipment or the component can fail before that time interval that is scheduled in your preventive maintenance program. Are we getting it? Then, conversely, on the flip side, it is also possible that the maintenance interval has elapsed. Okay, that is the PM interval has elapsed. Okay, PM says after 3 months do your change out. Then you go after 3 months and do your change out, only to find out that there is still some useful life in that component that you are changing out. Okay, but you have no other option because PM says change out. But you know, and I strongly believe that those of us experienced technicians that have been carrying out PM, there are some components, especially bearings and what have you, even seals, that PM says you change out, you should change out. When you remove it, you open up, you will see that the component, to you, you know clearly that that component still have useful life. Okay, but you have no other option, you will definitely change it. So what we are saying is this: it is possible that the equipment can fail before the normal PM interval where we need to do change out. Okay, then it is also possible that the equipment at that point of carrying out your PM, the equipment or the component has some useful life, which means we can still use it further. So if we do change out, those useful life will be a loss, okay, to your establishment, to your company. Are we getting it? Then if it fails before that PM time, remember that will have all the negative features of the run to failure. It can affect components and equipment downstream, even upstream of that particular failure point. Okay, so all of these are some of the drawbacks of the preventive maintenance or time-based maintenance programs. Are we getting it? So, one, failure before the PM time for that particular component, which can result to other expenses. Okay, that will be as a result of other components failing alongside, okay, that particular component. Then if the component has some useful life, the remaining useful life will be wasted, okay. So all of this put together will increase our maintenance cost or reduce our savings. So how do we take care of this? This is now bringing us to the main subject of our discussion, that is condition-based maintenance, condition monitoring. Okay, so how about if, that is, instead of basing our maintenance activities on time, how about basing it on the condition of the equipment or of the component, as the case may be? That is, we'll be monitoring, looking at the condition of that particular component or equipment, and then as the equipment is deteriorating, we'll be seeing it. Okay, so as it moves into the wear out region, we would have seen it, and then recommend maintenance before it goes into the failure region, irrespective of whether this is before the normal PM period or even after the normal PM period. What I'm trying to say is this: at the normal PM interval, okay, we do our condition monitoring or condition monitoring and analysis. We discover that that particular component still has some useful life. That means there's no need to change it. That will not be savings on our part. That is the cost, okay, of changing that particular equipment at that time, including all other downtime, including the downtime costs of the facility. So that will be savings, okay, to our facility at that particular point in time. So this now brings us, so this is what we are talking about, okay. So imagine now PM says the seal change out for this particular pump is 3 months. Now on the second month, you now see leaking seals. Okay, so if the seal is leaking in 2 months, it means that we have run that seal to failure. So how about if we have a technology in place that will help us to look at that seal and for us to know when the seal is failing? So even if it is before the normal PM period, we will see it failing, and then we'll do change out so that we will not have this kind of failure. Just imagine if this process fluid that is being spilled here is toxic to the environment, okay, or can affect the safety condition negatively of the plant, okay, or of the work environment. So we'll say that allowing it to fail would have resulted to other catastrophic events or conditions that will not be too good for our operations. So this now brings us, like we said earlier, to the other form of maintenance, which is maintenance that is based on the condition of the equipment. So which means that there are some parameters that we need to look at, okay, to determine the condition of the equipment. It could be pressure, temperature, it could be flow rate, it could also be the pH, it could also be the concentration of some of the process components, okay. So all of this will help us to determine, as we'll see later, the condition of the component, of our process, of our equipment, and of the entire plant, okay. So there are technologies that we can use to monitor each of these conditions, okay, or each of these parameters that will give us an idea as to the condition of the equipment. So we'll see all of this as we go along. So that is our focus, maintenance that is based on the condition. When the component is having useful life, there's no need to carry out any maintenance on it. When it is deteriorating, we know that the component is failing. Okay, we can now carry out maintenance, do change out. Okay, so you see that such change out is not based on time, it's based on the condition of the equipment. So assuming we have a rotating equipment like this, okay, assuming this is a pump. So on this pump we have the pump itself, and then we have the driver, which is an electric motor. So there are various parameters in this unit that we can be looking at to tell us the condition of this particular equipment. So now let's take the driver as an example. Okay, you know, in the electric motor, in the driver, we have windings. And one useful parameter that can give us an indication as to the condition of the winding is temperature. So we can look for a technology that will assist us to be looking at the winding temperatures. Okay, so we also have the delta T, the maximum delta T that that particular motor can withstand. Okay, if you actually do not want to deploy let me say high level technology, okay, you can use your local infrared camera or thermometer, okay, to be looking at the temperature on the frame. Remember, since the windings are on the yoke, which has direct connection with the frame, you see that whatever heat that is generated within the winding will be transmitted or conducted to the outside, that is the frame. So the frame temperature can give us an indication, okay, as to the winding temperature. So now, once we take that temperature, the delta T on the nameplate or on the electric motor data sheet, we do not want to exceed it. That is the difference between that temperature we took on the body and the ambient temperature. Okay, so you always see there, if it is delta T 40, so we do not, once the delta T is going beyond 40, we know that already that is affecting or will be affecting the windings of the electric motor. So whatever we can do to reduce that delta T, okay, we will do such. Then as the electric motor gets larger, we can put an inbuilt or install an inbuilt temperature sensor on the winding, okay, and then bring it out so that we can take the temperature, see the temperature condition of the winding externally. Okay, so that is getting the condition of the electric motor, and you know the windings in the motor, and you know also that temperature has a way of affecting the insulation. Are we getting it? So you see that parameter will give us an indication as to the condition of the winding and even the insulation of the winding. Then on the front cover and the back cover, we also have bearings. We can look at the bearing temperature too. Okay, remember, since the bearing is fixed on the housing, on that cover, you see that whatever heat that is generated will be transmitted to that housing. So we can monitor that temperature to give us an indication as to the condition of the bearing. So if the bearing is operating too hot, which we know is not too good for that bearing, it can also affect the operations of the bearing. Okay, and even the effectiveness of the lubricant in the bearing will affect it. So all of this can give us an idea as to the condition of the bearing, that's the bearing temperature. We can also be looking at vibration, as we'll see later. Okay, it's another parameter that we can be monitoring to give us an idea. Then coming to the pump side, we have the impeller, okay, and which is the main active component in the pump. We also have bearing on the pump side that we can actually monitor also. Okay, then the vibration too can give us an indication as to what is happening inside the pump. Then we can look at pressure, okay, the discharge pressure. Remember, if the impeller is wearing out, of course it will no longer be that effective, which means that the amount of fluid it will be transferring, okay, taking in from the suction to the discharge, will be going down, and that will affect the flow rate, to affect the pressure. So all of this will give us an idea as to what is happening inside the pump. So all of these are forms of condition monitoring. Are we getting it? And the suction pressure too, we know if it goes below some level, okay, it can cause the formation of bubbles in the fluid or process fluid, especially if it is below its own vapor pressure. Are we getting it? So if it is below its vapor pressure, that bubbles that will be generated can result to cavitation, and we'll see this as fluctuation on the suction pressure, discharge pressure, increased temperature, and also increased vibration, okay, on the pump. So all of these parameters will help us to look at some of these conditions of that particular equipment. So across strainer, okay, which is on this, which could be on the suction of which is on the suction of your pump. Okay, so how do we monitor the condition of the strainer? We look at the differential pressure, delta P, okay, between the inlet to the strainer and the outlet from the strainer or discharge from the strainer. So as delta P is increasing, that will give us an indication as to the fact that the filter is getting clogged. Okay, are we getting it? So once it's getting clogged, definitely that will increase the delta P. Okay, so which means that more restriction is now exerted on the flow or on the suction line through the filter. So if the filter is clean, you see delta T will be low, which means that the resistance to flow through the filter is reduced. So these are some of the parameters that we can look to give us some of the conditions of those important components, okay, of our plant equipment or of our process. So when we talked about condition monitoring, that is what we are actually looking at. So like in this case now, once delta P is increasing, what would that tell you? That the filter is due for change out. Now assume that maybe PM says 2 months, and you are now seeing that delta P has increased beyond what is tolerable, and we are yet to get to that 2 months. What will you do? Should we wait till that 2 months? Of course not. If we wait till that 2 months, it can cause further damage to our pump, because that increased delta P will reduce the pressure at the suction of our pump, can cause cavitation, will also affect what will come out from the pump discharge and affect other processes downstream. So we will not wait. We will change it so that our operations will become normal again. Okay. Then maybe PM says that same 2 months. At that 2 months, we see that delta P is still tolerable. What we will do? We will continue using that filter. You see that monitoring that condition will now help us to extract all the useful life from that filter, okay, which will be a cost saving to us. Cost of replacement, cost of labor, cost of downtime to our process, and in fact, there are some that can cause the downtime of the full plant, okay, of the whole plant. So, condition monitoring will help us to avoid all of this. So, beyond condition monitoring, we have another form of maintenance program or strategy that is based on reliability based maintenance program, as you can see on your screen. Okay, so the reliability based maintenance program, you look at the level of reliability you want, okay, and then look at how you can achieve that on all of the components in the system, okay, which means that you are looking at the system holistically. Let's take this pump for example now, okay. So you go beyond the pump and the motor itself, okay. You look at the system from the suction, wherever it is taking the suction from, okay, the source of the process fluid through to the pump, the driver, okay, then the discharge of the pump to the process where you are using to the process where that process fluid will be eventually used. Then on the driver side, if it is electric motor, you are looking at the motor itself and then the source of power to the motor, okay. So you look at it from the very source to the controller, then to the motor itself. So you look at the reliability holistically. So your goal is to ensure that each of these components maintain a level of reliability that will eventually affect the overall reliability of the plant or of your process. So these are the 4 basic maintenance strategies that we'll be looking at, okay. And we have known where condition-based maintenance or condition monitoring falls into, which is the condition-based maintenance. This, okay. So that is where we want to focus on now, condition-based maintenance. So the condition monitoring technologies that we can deploy, okay, in this kind of maintenance strategy is what we shall be looking at, okay.